Hello everyone, welcome back to Advent Code. In the previous video, I did part 1 of day 19, and this is going to be a shorter video. I'm not going to do part 20 right now, or day 20. I'm going to walk you through my changes to do part 2 of day 19, which I did not do on camera because it needed some thinking and I needed a rest. So for a reminder, we're given rules like this where, well, each of these rules kind of represent a very simple kind of function, and the input to these functions is one of these guys, and the output is basically accept or reject, a Boolean. So this function named PV says if A is greater than 1716, reject, otherwise accept. This one says if A is less than 2006, then go to QKQ, or call QKQ with the result. Otherwise, if M is greater than this, accept, otherwise go to this. And it asks basically for you to find out which parts are accepted and which are rejected. So this is what I had written. Oh no, this is, hang on. Spoilers, you've seen my part 2 solution briefly. So we have I talked some about initial and final encodings. I don't think I got this whole final encoding thing quite right, but it's sort of close and still kind of cool. Where this is our initial encoding, where we have the syntax tree, if you will, of the language that we're compiling, which is the list of functions that the workflow. The list of workflow functions, we're going to compile that into basically a Haskell function. But this is the closest thing there is to a syntax tree. You know, we're not going to interpret each line of the original input, right? We're not. Oh, there's my test input file. Get out of here. Oh, I guess I closed the regular input. Anyway, we're not going to interpret this whole line as written. We're parsing it first to understand what it means, and then building a syntax tree out of it using these algebraic data types. But then there's this compile function that takes a list of workflows and produces a function from part to verdict. So we wrote this in yesterday's video, of course. This is all still just review. We use an intermediate map to look up things in the workflow, but this map vanishes at the end of compilation. Not the compilation of our Haskell program, but the compilation of the workflow program that this compile function does. By the time we pass this function apart, all of the indirection through the map has already been done. For example, this compile outcome is the only thing that uses a map, and it doesn't take a part as argument. So by the time we call this function with a part, it's already looked up in M the workflow function for the label that you're going to. So the map will disappear. There are a couple of things. One thing that I think I was a little bit uncomfortable with when I wrote this, and that I ended up needing to change for part 2. So if I was right that I was a little uncomfortable about it, maybe that is a hint that something was wrong. Maybe I'm just misremembering, looking at the past with hindsight. But this function here is the only function that mentions parts in this whole compile phase, right? We take this condition and we compile its pieces. We compile the field into just a function from part to... Oh, that's not true. Compile field also mentions parts. It doesn't have an explicit p argument, but it takes a part here. Okay. So these two functions take parts. We compile the field, we compile the operator into a function, and the threshold is just an int. And it's just a little bit weird, isn't it, that like some of these steps don't really care about the fact that we're working with parts at all, and some of them do? And then so part 2 I mean, okay, and there's this big long parser here. Doesn't really matter. Part 2 of the problem asks us, well, don't just run your workflow functions on specific parts. Tell me all of the parts that would be accepted in the universe, sort of, right? They say, each of the 4 parameters that a part has can range from 1 to 4,000. How many unique parts does this entire workflow accept? And at first glance, it may seem like you can't really reuse any of this compile machinery. I didn't think of anything, like, at the time I had just read the problem. When I went away and thought about it some more, I came up with a way to reuse compile. But it kind of looks like, okay, you have to start from the bottom of the tree, the leaves, the accepts and rejects, and somehow work upwards from them to nodes that can reach them. And like narrow down what ranges could lead you to those outcomes. It seems complicated and confusing, and I didn't really have a good way to do that. But I realized that if we just rip out all the stuff that cares about parts, which is these functions, then the stuff above here is kind of a general function for asking questions about the list of workflows. And this, I think, is getting closer to the concept of the final encoding that I've meant to implement. So let's look at that first. This is not my complete solution to part 2 at all, but it's a partial step. I added in predicative types because, well, you'll see why in a moment. I changed the type of compiled workflow. Instead of just being a function from part to int, it's this kind of goofy type. It depends on handler. So basically in this compile thing, if we take out the 2 functions that mention parts, right? One of them is what to do with a verdict. Well, this sort of mentions a part. It mentions what it is you want the return value of this this function to be. And we also don't have a way, if there's no part input, we don't really have a way to combine 2 return values into 1 return value. So I take compiled workflow and say, if you give me a handler that knows how to handle R's, I can give you an R. I don't even need to know what R is. That's what this for all means, is you can pick any R you want. So if you can tell me what to do with a verdict and how to combine the results of 2 calls on this data structure, then I'll look through the whole tree for you and combine things the way you said, and when I get to a verdict, I'll use the handler you said. So most of this looks pretty much the same as it did before, except what has changed. I've added this K here. And there's one other change somewhere. Where is it? Combine. Oh, I see. Yeah. Right. No, all the changes are in this function, aside from the fact that I deleted the ones that were under it. So this K is the handler. We could call it H, but I think this is a continuation, basically. The type of compiled workflow looks sort of like the type of continuations. I don't know. I wasn't sure. I called it K. We're basically... well, whatever. I called it K. So to compile a step now, we have to say, okay, compile the outcome and pass it most of these functions can leave k as implicit, right? Compile workflow doesn't mention k. We could have written, like, it takes a k argument and calls the result with k. No? Maybe not. Compiled workflow has 2 value arguments. Shouldn't it though? Oh, no. No, because it returns a pair of things, I see. So we could have said, like, we could have explicitly handled the thing here. We could have said lambda k to all this and call it on k. You know, we could make the k explicit in all of these functions. It's simpler here. You can say, you can put the k in there and the k in here, right? And that's all fine. This is just simple eta reduction where we leave the function parameters implicit. If we're just going to take a function and then take a value and pass that value to another function, we can just like not do that. Here, though, we do actually use k, so it has to be a function argument. And that means that I have to pass it to compile outcome. I can't just return compile outcome. But so to compile a step, we say, okay, first compile the outcome. The condition is... right. Next... What is next? Oh, it's the argument here. Okay. So this is an already compiled outcome. And this is a thing we still need to compile the pieces of. So we call the user's combine function, which is combine of k, because remember k is the record that has combine as a field. And we just pass it the condition. You know, it's your job to figure out what to do with this condition. And then its second argument is compiling the outcome, and the third argument is compiling the it is the already compiled next step. So that's fine. And then all the logic that used to come after that goes in part 1. We just have these functions completely unchanged. And part 2 still isn't written at this point, but you know, we can stack run and observe that it still produces the right output. So, what about part 2? How do we reuse this general machinery? Now I don't have to touch compile anymore. But I did actually change input, which I hadn't done in part 1. I should have, or maybe in the last commit, I mean. Did I? Oh yeah, no, I had changed input and I hadn't noticed that. I parameterized it on its A type just so I could have a fmap, just to make things a little bit more convenient. Because I wanted to parse an input of uncompiled workflows and then fmap compile just to like change the first field. This is really kind of a stupid use of functor, but that's life. Oops. There we go. So now back to the actual solution to part 2, where again, I don't have to change this compile function at all. So here's where part 2 actually, oops, there we go, is. I basically want to like have the final value returned by our workflow action, in this case, shouldn't be a function from part to bool, or part to verdict, or whatever it was, but rather should be a list of conditions under which we would accept a part. I thought at first about like trying to somehow have it be a single map where like we describe the constraints on each field, and it's like, oh, A could be in this range to that range, but if it is, then X has to be in this range to that range or whatever. Maybe something like that could be possible, but it sounds very hard, and I think in the end it would be isomorphic to what I actually did, which is to return a list of, like, when we get to an accept node, we've got some upper and lower bound on each of the 4 parameters. And it really has to be, like, a single range. It can't be divided. And I think also there's never... I mean, I don't think it's a coincidence that there's never any duplication where, like, we count the same thing twice. Because... This is an important feature of the problem statement, I guess, that might not be obvious, is that I'm sure it was very intentional by Eric, but I didn't notice it until I was working on part 2, is that every time you evaluate a condition, you're splitting the search space like into 2 pieces. Not necessarily in half, but into 2 pieces. On the left side, or on one side, you have, you know, okay, this is what will happen if X is greater than 2746. And on the right side, you know that X is not greater than 2746. That's kind of sort of looks obvious if you're looking at this. Oh, if this condition fails, go here. But you could be forgiven for not like thinking too hard about that and saying, okay, well, I don't really know that much about X in this clause because this clause is about A. So when we get to JCL, we don't know much about X. But we do. We know that X wasn't greater than 2746 because if so, we would have gone to reject instead. Now, it might be that when we get to JCL via some other path, we don't have that constraint on X. But for the path to JCL that goes through GF, we have constraints on both X and A by the time we get there, right? Because we've tested A directly, and we've failed a test on X, so we have constraints on both of them. So I don't think there can ever be 2 different ways to get to an accept node with the same... with any overlap between the constraints. Because if there were, you would have taken a... like, you couldn't have gotten there by... Does what I'm saying make sense? If there were 2 different paths to an accept that had any duplication between them, there would have been some point at which you branched differently from one node when the condition you're testing was the same. So I don't think it's possible for there to be any overlap, which is important. Because that would lead to double counting here. If we had multiple ways to get to the same conclusion about, oh, we accept this range, then we would be double counting those. But I don't think there can be, and so we don't. Anyway, the point is... I just call the workflow that I compiled with a different handler, saying here's how to choose between 2 nodes and here's how to finalize, handling, you know, pretty simply here. If you reject, then there's 0 ways, zero constraint sets, which I think actually I gave a little type, yeah. I never used that type. You know, I could delete it, but I don't know. It's just kind of nice to maybe have here as a reminder of what the map we're working with is. And while I was working on this, I did have some optional type signatures written in here. But I don't know. I guess I could delete this. I mean, oh right. The reason I had universe as its own like thing is that like that way m.from list I don't have to evaluate every time we get to an accept node. I can just return a pointer to the same map. It's not an important optimization, but it seems like a reasonable one. I'm using v2's event to like as my pair, where the first one is the lower bound and the second is the upper bound. So choose, require, and forbid are kind of my least favorite functions here. Choose takes a condition and where to go if the condition is true and where to go if the condition is false. And it basically says, well, you know, you are adding together two lists. First, look at the yeses, and for each one, adjust their constraints to require that f meets this limit. And also, look at the no's, and for each one, adjust their constraints so that f doesn't meet this limit. And so require and forbid like clearly have a lot in common, but there wasn't any pretty way that I saw to abstract between them, so I just wrote them out by hand. Yeah, we're adjusting the map with f. Using over from lens. So, of course, because it's Edward's library, v2s also are lenses. Or, no, the x and y accessors also act as lenses. Or they're not even really accessors, are they? Maybe. I don't know. I think so. But they're these really... lenses are really powerful, and I only barely understand them. One thing you can use them for is to do like updates in a structure without having to pattern match, pull it apart, edit something, and then put it back together. So over basically means apply the following function to the field indicated by y, and then give me back the data structure that was there with that one change made. So over y, we're going to min with limit -1. So if some field has to be less than limit, then we need to decrease the upper bound, which is y, so that it is at most limit -1. Because if we allowed limit, then we wouldn't know that y is less than limit. And similar stuff here, you know, there's some possible off by one errors that you have to be careful of. And it's a little confusing to think of, you know, stuff in this way, but it's restricted to just this little section here. Count options is pretty simple. We just look at the elements of the map, which are the 4 ranges for the 4 fields. We say how many options does each field have, and we multiply together the result. The field options, you subtract high minus low plus 1. I put a max 0 in here because I was worried that somehow you might end up in a situation where low is greater than high, and yet you would get... I think that's possible, right? Let's take this out and see if I still get the right answer. I don't think I should. It does look like the same answer. I'm looking at the Advent of Code website here. It starts with 135506 and ends with 6673. Yeah, same number. But I don't think that's justified. I think that you could construct a puzzle workflow where, like, there's a state you could reach that, like, first tests that x is greater than 100, and then you say, oh, if that's true, go to this other state, and that state tests that x is less than 2. I don't know. So it's greater than 100 and less than 2, and if so, accept. Like, that's a valid workflow. You'll never reach that node, but it's valid to express that is a way to do the computation. And if somebody did write a program like that, then we would get high minus low is like... well, the high would be 2, and the low would be 100. And we'd get this negative number. So I put a max 0 in here to just make sure that we count that as, no, it can't happen, and not as, oh, actually it's so unhappenable that other ways you could get here become impossible. So the nice thing about this, I don't know, it's just a cool function. I like it. But one cute little thing you might not have noticed is that now I moved the compilation of the workflow from part 1 into the parser, into prepare. So input, part 1 takes an input of compiled workflow. So it's already been compiled. It's already been run through this like map step. Or it's been partially compiled, right? It doesn't have the handler for condition. We start by passing it, oh, here's how to finish compiling conditions, please. And this thing says, it also takes a compiled workflow. So prepare actually does the compilation once and then passes it to part 1 and part 2. So this is proof that, like, oh, the compiled workflow type is flexible enough to handle multiple different traversals over the program represented by the list of workflows. And I tried looking around to find, like, what is the theory that I'm, like... I've clearly implemented some ad hoc special case of a more general thing. And I'm sure I've read about what that more general thing is, but I couldn't quite nail it down. So, like... Is this compile, like... This looks a lot like a continuation, maybe? Am I re-implementing Kant? Is it some Yoneda shit that I don't understand? Is it code density? These are things I encountered while trying to search for, like, what is it that I'm doing here? And I don't know. I don't quite understand it. If someone out there knows, oh, here's the theoretical way to, like, to formalize what it is you've done here, I'd be interested to hear about it. Because it's one of those things I'm always struggling with is, like, I'm kind of at the, I don't know, the boundary of my understanding of what's going on with some fancy types here. I don't know, that's not really fair. I think these types are like, yeah, you don't see them every day if you're not familiar with Haskell, or even if you are, you don't often need them. But, like, yeah, I understand this. I understand this. I use it on purpose. But I don't know, like, I don't know. I tried reading how delimited continuations work, and it's one of those things I have to relearn every year and a half, and I still never really get it. And since I'm not calling call CC here anyway, I don't think it really helps to think of things in terms of continuations, even if it were legal, which I'm not sure it is. So, I don't know. Like I said, if anybody knows what it is I've cooked up here, I'd like to hear about it. So that's all for today. Or, well, for this video. I guess in several hours, the video for part 20, for day 20, or maybe just day 20 part 1. I don't know. I haven't read it. Will not be delayed. There's going to be 2 videos in the space that 1 video would normally take up. Anyway, hope you guys enjoyed. Thanks for watching, and I'll see you next time.